Hello, my name is Jonas Jalowy, and first of all, thank you for taking the time to watch this short presentation about the fluctuations of the magnetization in the block POTS model. And since I want every second of this video to be worth watching, let's just directly jump into a simulation. And as always, please just feel free to interrupt me at any point by hitting the pause button or by getting back to this illustration if needed. So what you see here is one realization of the block POTS model, which is a spin system divided into, let's say, 3 blocks, where each spin can take one of 3 different values: blue, mint, or yellow. And each block itself behaves like a mean field POTS model. That means that all spins are interacting with each other according to some inverse temperature beta. If you don't like spin systems, you can also think about a model for social choice, where each citizen in a state is voting for either a blue or yellow or mint colored party, but is also affected by some kind of peer pressure from all the other voters. Moreover, all these spins are influenced by the spins in other blocks according to a different interaction, let's say alpha. And what we will be interested in is to look at different realizations of the magnetization. The magnetization is this long vector down here, which tracks the proportions of each color in each block. And in the so-called high temperature regime, we expect the uniform vector to appear in the large N limit, meaning that roughly 1/3 of all the spins will be colored blue or yellow or mint. And one realization of the magnetization then might look like this, where you see that there are a bit too many blue spins in the first block, but because of the positive interaction with the other blocks, there are also a bit more blue spins in the second and in the third block as well. And what I would like to convince you in the next few minutes is that though this looks like a random mess, the dependencies of the fluctuations are a very non-trivial and interesting object to study. Okay, let's begin with some mathematical notation. So we look at a spin system with n many spins, which can take q many colors and are divided into s many blocks, sk. And then the Hamiltonian of a configuration omega consists of 2 parts, where the first part describes interactions between spins in one and the same block, interacting with an inverse temperature beta. And the second sum similarly counts the number of equal spins in different blocks interacting with an inverse temperature alpha. Special cases that you should have in mind are, for example, alpha equal to beta. Then we get back the classical mean field POTS model. And for alpha equal to 0, we're looking at blocks of independent mean field models. Then, as usual, the Gibbs measure is a probability measure defined on the space of configurations, which favors configurations of low energy. As I've been telling you already, we are interested in the magnetization, which just counts the number of, let's say, C-colored spins in the kth block relative to the size of the kth block. And we should also define the interaction matrix A, and one special interaction matrix is given here, A alpha beta, which just has beta on the diagonal and alpha everywhere else. And if we now give this matrix a bit more structure, as we will see later, then we can also write the Hamiltonian as a function of the magnetization, meaning that the magnetization is an order parameter for this model. Note that the research on block spin systems began with the block Ising model corresponding to Q equal to 2. Yeah, now I'm happy to present our central limit theorem, which states as follows. Let us consider an interaction matrix as given in the previous slide. And we look at the so-called high temperature case, meaning that the spectral norm of this matrix is smaller than some critical parameter. If we consider asymptotically equal block sizes, as we have been seeing in the simulation in the beginning, then as the system size grows to infinity, the magnetization concentrates around the uniform vector, and the fluctuations are given by a Gaussian distribution with some explicit covariance matrix, which just depends on all the parameters that you see here. Here, this script S matrix is basically the matrix of all the block sizes, but as I mentioned already, is given a bit more structure by building the Kronecker product with the identity matrix, and similarly, we will build the interaction matrix script A by taking our interaction matrix A and building the chronicle product with an identity, which basically just gives every element of the interaction matrix one copy of the identity matrix. And with the help of this structured matrices, we can also state a more general theorem where we consider arbitrary block sizes and any positive definite matrix A with positive entries. Then we get the same central limit theorem as before in the very high temperature case where the spectral norm is smaller than another number here. At this point, I would like to point out a subtle difficulty which makes the Potts model much harder to study than the Ising model. Due to the first order phase transition, we will confront 3 different thresholds that coincide in the Ising model, and 2 of which are already visible in these 2 theorems here. Okay, in the remaining minutes, I would like to quickly tell you about the proof. And the idea is to make use of the so-called Hubbard-Stratonovich transform to use Laplace method. What you do is you look at the moment generating function of the rescaled magnetization, but modified with an independent Gaussian vector Z. And if you take the correct distribution of this Gaussian vector, you will find that this random variable actually has a density that is given by the exponential of some function phi. And now it remains to analyze this function phi, which, as always, splits into one energy-like part and one part that corresponds to an entropy. For now, let's just assume that we already found a unique minimizer of this function phi. Then we could use Laplace method, which in this case just tells us that this moment-generating function will converge to an integral of the exponential of the Hessian of phi. But this limit is nothing but the moment-generating function of a different Gaussian distribution, so we can explicitly write it down. On the left-hand side, we still have this independent Gaussian vector Z, but since it's independent, we can just put it to the other side. And this is exactly what we define as the covariance matrix, and that's all we needed to show to prove the central limit theorem. If you're familiar to large deviation theory, then you might believe me that with a bit more work and using Gardner-Ellis theorem, you can also prove a moderate deviation principle for fluctuations between the central limit theorem and the regime of the large numbers. Of course, finding this minimizer and proving that it's actually unique is the hardest and most technical part of the proof. So I will tell you a tiny bit about how we achieved that. This minimizer satisfies some critical equation. If you play a bit with it, it's possible to show that the minimizers are structured like a convex combination in an S-dimensional parameter t here. If you look at the function phi as a function of the variable t here, then you will, in this case, for example, see directly that the minimum is uniquely achieved at t equal to 0, and this corresponds to our favorite candidate psi because it's just the uniform vector psi. But what happens if we now increase the spectral norm of the interaction matrix A? Then you will see that at some point a new minimum will appear, which is one of the thresholds I've been telling you about in the beginning. And if we continue to increase the interaction, then at some point the new minimum will be the global minimum. And if the interaction matrix becomes bigger and bigger, then at some point our favorite candidate t equal to 0 will not even be an minimum anymore. And of course, this is all something that you need to prove. The first fact that should be clear from the picture, at least, is that the Hessian is positive definite around the uniform vector if and only if the spectral norm is smaller than this threshold q. Then if the spectral norm is smaller than 4q minus 1 divided by q, then this is the unique minimizer of phi, which we can prove by using a fixed point argument. And by using convex duality, the large deviation principle by previous work, and the relation to the classical non-block Potts model S equal to 1, you can also show that under the assumptions of theorem 1, if the spectral norm is smaller than the critical parameter, then the unique minimizer is also given by this uniform vector. Yeah, and these are basically all the ingredients that we need in order to prove the central limit theorem, where in the future, of course, we would like to get rid of the positive entry assumption and get closer to the critical or even with the low temperature regime, because then we could understand the following very interesting frustration phenomenon, which happens if you look at more blocks than colors available, and if you have negative interaction between the blocks. So I just leave you with this simulation here, and thank you very much for your attention.